All right, so in the previous online lecture that we did, we talked about factorial experiments and briefly discussed what they were, but we really focused on whether interaction was present or not. So in this lecture, what we're going to focus on is the different types of factorial experiments. So we're going to look really briefly at a completely randomized design, a randomized block design, and a split plot design, all with multiple factors. So some of these slides are going to look familiar to you. I just want to reiterate it in a different context than what we talked about interaction with. So keep in mind that factorial experiments are where you are really examining the effects of two or more independent variables or treatments on some sort of response. So this could be like testing a level of mineral supplements in addition to testing a level of feedstuffs. So with the factorial experiments, we move from testing one null hypothesis in a single factor design to three null hypotheses in a factorial experiment where we have two levels of treatments. So our first null hypothesis is that levels or performance within factor A don't differ. Second hypothesis is levels or performance within factor B does not differ. And third is that there's no interaction present between factor A and factor B. So with these types of experiments, if we were setting up a completely randomized design, meaning that we don't have any known source of variation, we're just we have a homogeneous population or for our sample size. So we're just truly testing the effects of two different levels of treatments. And so if we had three levels of a mineral and three levels of a feedstuff, and whereas mineral was factor 1 and feedstuff was factor 2, in order to figure out what type of factorial design we had, we would just multiply the levels within each treatment. So we have 3 for factor 1, 3 for factor 2, 3 times 3 is 9. And so this really sets up a 3 by 3 factorial experiment. And so those 9 different treatment combinations lay out like this, where we have a factor for treatment 1 across the top and a combination for our factor for treatment 2 across the left-hand side, resulting in 9 combinations for our treatments. So if we wanted to replicate these treatments 4 times, meaning we had 4 experimental units per treatment, we would then be able to figure out how many different experimental units we would need. So we had 2 factors times 2 treatment levels times 4 replications gives us a combination of 16 experimental units. So in the previous lecture, we talked a lot about interaction and what that was. Just to review that very quickly, interaction is where the effect of one factor on the response variable does not remain the same for the second level or the second factor. So in other words, the effect of factor 1 is not the same across all treatment groups. And we can identify interaction pretty steadily and very easily once we have it into an analysis program and are able to graph it out. So once we graph out the treatment means for the different combinations, then we can actually see if the lines from mean to mean within the different categories cross. If they do not cross, we don't have interaction. However, if they do cross and we get something like this or like this, we do have interaction, meaning that one category of a treatment level was not acting the same among all treatment levels of the second factor. So interaction can take on a couple of different forms. The most common and easily visualized one is where the lines for the means cross. However, we can also see if interaction in lines that don't cross but are not parallel, like shown in the bottom of the slide. So we know that interaction is going to have a p-value associated with it. So if our interaction term in our ANOVA analysis is not significant, then we interpret that as we ran 2 separate experiments. However, if the interaction term or p-value in the ANOVA analysis is significant, then we have to interpret that as we did not run two separate experiments and um, have to view the results of our project through a different set of lenses. And then in the previous lecture, we also talked a little bit about what our ANOVA tables actually look like. So in this case, our interaction term is not significant, therefore we ran two separate research projects, one where we tested factor level A and there was significance, and one where we tested factor level B and there was also significance. However, if we do a project and we get an ANOVA analysis like this, you guys can ignore this stuff over here on the side. That's what I was going to have us do in class. But if we ran this research project through an ANOVA analysis and got this printout, what we end up finding is that our interaction term is significant. Therefore, we cannot assume that we ran two separate studies, one for factor A and one for factor B. But it's not that we throw this whole project away. We just have to look at the results through a different set of lenses. So again, here, this is a good practice point, a good point for you guys to pause this video and reason through what you can conclude from the statistical analysis. So when you do that, you should find that factor A and factor B interacted, and that is designated by this term here. So this term is way less than 0.05, meaning that we did not run two separate experiments. So with that context, if you look at the means or graph out the means on this chart, you should be able to visualize what is actually going on. So let's switch gears a little bit. That last example where we were looking at minerals and then feedstuffs as our two levels, that was in the context of having no outside variation. However, we can account for a known source of variation similar to how we did it in a single factor design in a multi-factor design. And that means that we are just running a randomized block design to factor. And so the next series of slides is going to look at that. So if we were to put this in the context of an example where we were interested in soybean yields as measured by bushels per subplot unit, we would actually lay it out over 3 blocks. So let's assume that our known source of variation is the soil gradient. So factor A would be testing 2 levels of fertilizers, and factor B would be testing 3 layers or 3 different soybean varieties. So the number of treatment combinations that you would need gets pretty significant pretty quickly. So we've got, again, our field 1 and or our fertilizer 1 and fertilizer 2 scenarios, and then we've got our soybean varieties. So soybean variety 1, 2, and 3. And so our blocks are going to be over the soil gradient. So we've got soil gradient number 1 here, soil gradient number 2 here, and soil gradient number 3 here. And so we can assume that this is going to be a coarse soil moving towards a fine soil. So within each block, each treatment has to appear. So we've got fertilizer 1 and fertilizer 2, both being tested within the context of soybean variety 1. Then we have fertilizer 2 and fertilizer 1 being tested within the context of soybean variety 3 and 2, and the complements are down here on the bottom. So if you look within each factor, you will see that each treatment combination shows up once within each block. Very similar to what we learned about in the soil or in the single factor analysis. So after we collect our data on yield, we run that data through an analysis of variance. Our analysis and variance table gets much bigger. You can see the source of variation now includes the information for factor A, which in this case would have been fertilizer, factor B, which would have been soybean variety, the interaction term between factor A and factor B, and also a term for the block. So what we can assume here is that, we'll start down here at the bottom, is that since the block probability or p-value is less than 0.05, we know that that block was significant and we had different performance levels within our treatment groups based on where it was positioned in the field in the soil gradient. The interaction term is not significant. It's not less than 0.05. So that tells us that we ran two separate trials where we can assess factor A and factor B independently. So in this case, because the interaction is not significant, we can reject the null hypothesis that there are no differences between fertilizer levels, and we can reject the null hypothesis that there are no differences between soybean varieties as well. So again, with a RBD-2 factor design, we have to ask ourselves, how realistic is this design for the problem at hand? So some things to take into consideration are, how is the project going to be laid out? What kind of expense is associated not only with the materials needed, but also with the labor that it's going to take to maintain the plots or maintain the fields, as well as the labor. And you have to also take into consideration efficiency. So in the context of this example here, if there was need to look at the efficiency or the yield production within a certain fertilizer group and its effect on soybean variety, and that could actually be translated to the general industry, then there's going to be then there is a need to actually test those combinations in a research scenario.